When you're conducting an analysis of variance for a complete randomized design, you want to assure the randomness of the design to answer the question. You want to ensure the independence and randomness of samples, right? So you've got check your replications, check your block. I now collect my data and I need to check for normality. Remember the normal curve? Spent a lot of time on that. I want to make sure that my data is normal. I want to create an analysis of variance table, and I want to conduct multiple comparisons for the means. Okay. And if the null hypothesis is not rejected, I will need to consider possible explanations, keeping in mind the kinds of errors you can get. And I'll mention the type of errors. We did mention them the other day. I'll mention them again. When we start with the null hypothesis, the statement that the thing being studied produces no effect or makes no difference. In other words, the cultivars don't differ. Something like the diet has no effect on people's weight. Okay. And the intent is to run an experiment which produces data to show that the thing under study does in fact make a difference. Now what happens is if your data are not normal or there's a bias of any kind, you can make what they call type 1 and type 2 errors. Type 1 error is the incorrect rejection of a true null hypothesis. In other words, you get a false negative. So I say to you the cultivars do differ. In reality, they do not differ. That's a type 1 error. And if your trial design is incorrect and your data are not normalized, it's very easy to make these kind of errors. Type 2 error is the failure to reject a false null hypothesis. In other words, you have a false negative. So I'll tell you now the cultivars don't differ, but in fact they do differ. Okay. So it's essential that you make sure that your data are normal and that your trial layout, your measurements and everything else are correct. So there we have a normal distribution. Excuse me. There we have some skew data. If I do an analysis of variance on that, I could pick up anything. I need to get my data into that kind of format. Now, most of your stats programs, and if I don't get through it today, I'll run an analysis of variance in GenStat tomorrow just to show you, have some kind of normality testing. One of the ones that is used quite often is what they call the W statistics, a Shapiro-Wilk test, and that will assess whether the sample of data comes from a normal distribution. So you'd put your data into a stats program, and depending on the probability value you get, it will tell you whether your data are normal or not. So that one there is less than 0.05. Remember, we always work on the 95% probability. Well, as a rule, not always. Okay. So there the data are skewed. There the data, you can see it will tell you if it's normal or not. Okay. So based on that, you will then decide whether you're going to transform your data or not. There are a couple of other tests. You have Bartlett's test, which is very common. That tests for the homogeny of variances, and there are various other ones like Levine's test, Brown's test, and so forth. Okay. Every stats program will have options, and they all come down to the same thing. The question is, are our data normal? Okay. So that's the first point I want to make, so that you do not make incorrect assumptions, or what we call type 1 and type 2 errors. Okay. If your data are not normal, then it's important to decide which transformation you're going to use. Now, very often, a logarithmic transformation, log 10 or the natural log, it doesn't matter, will straighten your data. Square root is often used for count data, and if we have data that's in form of percentages, we use argsin, where we actually transform the percentage into a degree. Okay, and that will then hopefully straighten your data. You do have situations where you can transform it as much as you like, and it doesn't work. I've got a student with one of those problems.